In this video, we shall look at the phenomena of interference in thin films. Let's assume that we have the following thin film. We exaggerate the scale, of course. The thickness of that thin film is T. Let's assume the index of refraction of this thin film is N1. The index of refraction of the medium on which it is resting is N2. And this is quite simply air, with index of refraction equals to 1. Let's look at the following light ray. It strikes the thin film and will get reflected like that, following the law of reflection. There is a portion of that incident ray that gets transmitted into the film like that and reflected from that surface, like that, and out in the air. These two reflected rays, let's call them ray 1 and ray 2, will interfere and produce interference patterns along the site of observation. So if someone is looking from here, they will see the effect of that interference, namely successive bright and dark fringes. The question is, what are the conditions for these bright and dark fringes to occur? Let's remember, we are concentrating on ray 1 and ray 2. To answer that, it's important to realize that as the light wave is reflected off a surface like that, it may undergo a half cycle phase change upon reflection. So its phase may change by 180 degrees or pi radian, or half a wavelength. Let's say it is initially traveling in a medium with index of refraction N1 and index of refraction of the second medium is N2. If N1 is greater than N2, then there is no phase change. However, if N1 is less than N2, then there is a phase change by that amount, namely 180 degrees or pi radian, or half the wavelength. So let's get back to our original sketch. The path length difference of these two rays is quite simply 2t, namely this is t and that is another t. Now of course that is only true if the incident is almost a normal incident. But in this sketch we are exaggerating the figure. But we have to understand that this analysis is for almost normal incident. Now let's get back to the conditions. Let's assume ray 1 has 0 shift and ray 2 has 0 shift. Or ray 1 has half a cycle shift and ray 2 has half a cycle shift upon reflection. Then this condition that we have written here is the condition for constructive interference, and destructive interference is given by that condition. So to repeat, this is provided that neither or both have a half-cycle reflection phase shift. However, when only one of the two waves has a half-cycle reflection phase shift, then the top equation represents the condition for destructive interference, and the bottom one represents the conditions for constructive interference. So they flip. To understand this, let's look at the following problem. What is the thinnest film of coating with index of refraction 1.48 on glass, whose index of refraction is 1.59, for which destructive interference of the green component of an incident light in air can take place by reflection? So basically what you have is that is air. This is the coating with index of refraction of 1.48. This is glass with index of refraction of 1.59. The thickness is T. The question asks, what is the minimum value for this T must be so that destructive interference of the green component of that white light can take place by reflection. So you have reflection like that. This is the incident and this is the reflected ray, the transmitted, and then again the reflected ray. So ray 1 and ray 2 would interfere to give a destructive interference. So what should the minimum value for this thickness be for that to occur? Let's see if there is any phase shift for ray 1. It is traveling in air and then get reflected by a medium with index of refraction 1.48. So the first medium, whose index of refraction is 1, is obviously less than 1.48. That means there is half a cycle phase shift for ray 1. What about ray 2? Ray 2 gets reflected here. That means initially it's traveling in the film or the coating, and it hits the reflective surface whose index of refraction is 1.59. So since 1.48 is the index of refraction of the first medium and it is less than 1.59, which is the index of refraction of the second medium as far as ray number 2 is concerned, it will also go through a half cycle phase change. So that means the condition for destructive interference is that the path length difference between ray 1 and ray 2, which we know is 2t, must be the same as m plus half times the wavelength of that light ray in that coating. So that means the thickness is given by lambda over 2, m plus half. Now lambda is the wavelength of that light inside this coating. The wavelength of green component is 500 nanometer in air or in vacuum. So within that coating, the wavelength would be 500 nanometer over the index of refraction of that coating, which is 1.48 in the unit of nanometer. So we can write T equals to 500 nanometer. So turn that into meter by multiplying 500 with 10 to the power minus 9 over 1.48, and then there is this 2 here, times m plus half. So from this expression we see that T is minimum when m equals to 0. So by setting m equals to 0, we obtain the following number for T, which is the minimum value of T. And that value is 8.44 times 10 to the power minus 8 meter, or in the unit of nanometer, 84.4 nanometer. And that solves the problem. Thank you for watching.